With the available SIEMENS 4 protection relays, all conceivable generator applications are catered for. Applications ranging from conventional thermal power stations to combined cycle power stations up to power stations using non-conventional energy sources. As an example, we would like to demonstrate a protection application for a generator with a rating in the range from 10 to 20 MVA. The generating unit consists of the generator and the unit transformer. Two multifunctional protection relays are applied to achieve redundancy. A 7UM62 with a basic scope of functions for protection group 1, and a 7UM61 with complete scope of functions for protection group 2. The functional mix of the two protection groups was selected so that should one of the two relays fail, the generator can still remain in service with adequate protection. For this reason, some protection functions are duplicated. The overload protection, the unbalanced load protection, the reverse power protection, the under-excitation protection, the fuse failure monitor, the overvoltage protection, the frequency protection, the over-excitation protection, the rotor ground fault protection. Different techniques for the short circuit protection were implemented in the two groups. In Group 1, an overall differential protection is applied. In Group 2, on the other hand, impedance protection is used. This covers the generator as well as approximately 70% of the transformer. The inadvertent energization protection is also very important. If closing onto a stationary machine accidentally occurs, this function switches off the generator without delay. Within a power system, the bus bars constitute the energy nodes of the system. This further emphasizes the importance of reliable protection against fall damage. A low-impedance busbar protection scheme is used as a demonstration example. It is far superior to high-impedance busbar protection, in particular when multiple bus bars are to be protected. When using conventional technology, the secondary currents of the current transformer must be switched over from one measuring system to another using isolator auxiliary contacts when transforming the bay to another bus section. The 7SS52 busbar protection has an integrated isolator replica in the software of its central unit. Therefore, current transformer circuits no longer need to be interrupted. Furthermore, the isolator replica is continuously checked to ensure that it's plausible. A further advantage: in the indicated protection scheme, the current transformer of the feeder protection may also be used for the busbar protection. This is possible even if the current transformers of the individual bays have different transformation ratios. In the event of circuit breaker failure, the central unit 7SS522 has an integrated circuit breaker failure protection. Following a measurement with a busbar protection system, it forwards, after a short delay, the trip command from the feeder protection to the adjacent circuit breakers. The consequences of a fault are therefore limited. Transformers are amongst the most expensive plant items in power systems and power stations. Their failure usually results in extreme losses, which can only be limited with adequate protection. An example of SIEMENS 4 relays for transformer protection is shown by means of an application to a 1.5 breaker arrangement. The applied differential protection relay 7UT61 also covers the stub. If the obtained sensitivity is not sufficient due to the large transformation ratios of the CTs, a second, more sensitive protection may be connected to the bushing CT of the power transformer. A restricted ground fault protection is integrated in the 7UT61 using a separate measuring input. This provides protection coverage for faults on the low voltage side of the transformer. Although the 7UT61 already contains a backup overcurrent protection, a separate overcurrent relay of the type 7SJ61 is preferred in this concept to achieve hardware redundancy. Thereby, a backup protection remains in service even if the auxiliary voltage fails. Apart from its main task of short-circuit protection for the transformer, the relay on the high voltage side also provides protection against overload. The negative sequence measurement of the short-circuit current provides sensitive backup protection with a setting threshold below nominal current. It comes into effect for all non-symmetrical faults on the low voltage side of the transformer. The relay also measures the ground short-circuit current in the transformer neutral on the low voltage side. Thereby, it assumes the role of standby protection in the event of all downstream ground fault relays failing. The total fault clearing time for line faults should not exceed 100 milliseconds even with single component failures within the protective scheme. This requires full duplication of all equipment right from the instrument transformers through the protection relays, teleprotection channels, station batteries, and trip circuits. Our example shows a redundancy concept for the protection relays and the transmission paths. In this concept, we use protective relays with different measuring techniques. Relays of the type 7SA522 for distance protection, and relays of the type 7SD52 for line differential protection. The distance protection relays obtain their measured signals from the respective local substation and also provide remote backup protection. The line differential protection relays are completely phase selective in both measurement and tripping. To ensure this absolute phase selectivity, communication paths with large bandwidth and numerous available channels are required. The data is therefore preferably transmitted via fiber optics or per line-of-sight radio signals. A separate communication channel is provided for the distance and line differential protection. If one channel fails, the other protection scheme remains in full service. With the Model 7SD5, you have differential and distance protection as fully fledged functions, all in one protection device. This combination offers a maximum value of selectivity and availability, and at the same time, enables cost-effective protection concepts. Feeder bays can be found in a number of areas within the system structure. Correspondingly, the implemented protection principles are numerous and diverse. An example for feeder protection, as found in rural supply zones with overhead lines, is shown here. In this application, overcurrent protection relays combined with multi-shot auto-recloser function are often used. The 7SJ61 multifunction protection relay is therefore applied in our example. The instantaneous overcurrent function of the relay initiates tripping during short circuits on the overhead line with no delay or a short delay just exceeding the fuse operating time of the feeder fuses. Following the first short dead time, the auto-reclosure initiates reclosing. If the fault was of a transient nature, the reclosure is mostly successful and the short circuit is cleared. If, however, it is a persistent fault, the instantaneous overcurrent function immediately initiates a retrip. During the second, now longer dead time, the logic in the recloser or the sectionalizer separates the faulted circuit from the feeder. Thereafter, the auto-recloser switches the feeder back on. If the fault has been removed, the function automatically resets. If the reclosure was unsuccessful again, the time-delayed overcurrent protection function in the relay finally trips the fault. The protection concept for a double circuit line is used as an illustrative example of feeder protection in the industrial environment. This concept is preferably used for the interruption-free supply to important consumers without significant backfeed. A non-directional overcurrent time protection function is applied in the 7SJ61 relay on the feeder side of the in-feed transformer. This function provides protection against phase and ground faults on the feeder. If the feeder is a cable, the thermal overload function is activated. Generally, this provides an alarm to the control center when an overload condition arises. In the event of the first alarm stage, sufficient time remains for the implementation of operational steps. A directional overcurrent time protection function is implemented in the 7SJ62 relay, applied at the opposite end of the feeder. This function provides non-delayed tripping in the event of faults on the feeder. The ultimate fault clearance is obtained when the non-directional overcurrent time protection at the feeding station trips with a time delay. Various types of motors may be protected with SIEMENS 4 relays. The following example demonstrates a protection concept for a motor with medium rating in a system with high ohmic neutral grounded network. All required functions are provided by one relay of the type 7SJ62. Due to the extremely small ground fault currents flowing in the event of a ground fault, the ground fault current is not measured via summation connection of the phase current transformers. A core balanced current transformer is used instead. For secure ground fault detection, the 7SJ62 utilizes the zero sequence voltage of a broken delta winding of the busbar voltage transformers as an additional criterion. The instantaneous overcurrent function of the relay trips without time delay in the event of short circuits. Furthermore, the negative sequence component of the load current is also measured to detect broken phase conductors and voltage asymmetry in the system. In the event of a locked rotor, the locked rotor function prevents overheating of the motor with its trip after short time delay. The load cycles of the motor are registered by the thermal overload function of the relay. Heating and cooling cycles are evaluated with separate time constants. This way, the capacity of the motor can be fully utilized.